Hello, everyone. In this video, we are going to discuss integration by parts. Integration by parts. So far, we have learned integration rules involving elementary functions. However, for other elementary functions and products involving elementary functions, integration is not as straightforward and easy to do. The following discussion presents an integration technique called integration by parts, which transforms a complicated integral into a product and a simpler integral that is easier to integrate. For an indefinite integral, integration by parts is given by the following formula. The integral of u times dv is equal to u times v minus the integral of v du. But first, the integrand has to be separated into two parts, where u is an expression in terms of the independent variable, and dv is another expression in terms of the independent variable multiplied by its differential. Apply integration by parts to express a complicated integral into a product and a simpler integral. For this reason, choose u as the part of the integrand that has a simple derivative, and choose dv as the part of the integrand that has a simple integral. This means that the formula for integration by parts can also be written in terms of the independent variable. While there is a product rule for differentiation, there is no product rule for integration. However, there is a connection between integration by parts and the product rule of differentiation. Derivation of integration by parts. Consider the product rule of differentiation for two functions u and v. In differential form, the product rule is written as follows. If we integrate both sides of the equation and solve for one of the integrals on the right side, say u dv, we get the integration rule for integration by parts. An indefinite integral can be solved using integration by parts if using the formula results into a product and a simpler integral. Wrong choices for u and dv can result into an even more complicated integral. Strategies for integration by parts. Choose u such that it has a simple derivative, while dv has a simple integral. In other words, choose them such that the integral of v du is simpler than the original integral. For instance, in the integral of x sine of x dx, let u as x, which means du is equal to dx, and let dv as the sine of x dx, which means v is equal to the negative cosine of x. Plugging these expressions into the formula leads to a product and an integral which is simpler to integrate than the original integral. However, if we choose u as the sine of x, and dv as x dx, the formula produces a more complicated integral than the original integral. As another example, suppose we want to find the integral of x times the natural logarithm of x dx. If we let u equals the natural logarithm of x, and dv equals x dx. Applying integration by parts results to an integral that is now simpler than the given integral. Choosing u as x and dv as the natural logarithm of x dx. Would lead to a more complicated integral, which may require another use of integration by parts. Another strategy in applying integration by parts is to try to convert the integrand into an algebraic expression whose integral can be found using basic integration rules. As an example, to find the integral of the inverse sine of x dx, let u as the arcsine of x, which leads to du of 1 all over the square root of quantity 1 minus x squared dx. And let dv as dx, which means v is equal to x. Substituting this expressions into the formula leads to a product and an integral of an algebraic expression, which can be found using the general power formula. Another technique is to use integration by parts repeatedly. Consider the following example. Try solving using integration by parts. And substitute the required expressions into the formula. The resulting integral is not simpler than the original integral, however, it did not become more complicated neither. So apply integration by parts again. Use integration by parts repeatedly if needed, as long as the remaining integral is getting simpler or similar to the original integral. Distribute the constant multiplier and move this integral to the other side of the equation and combine. And then solve for the original integral. In addition, we can use integration by parts with substitution rule. Please consider the following integral. Notice that the integrand is an exponential function of an expression rather than of the independent variable, which would have meant applying an integration rule directly. So, introduce a new variable as the expression that makes the integral complicated. Compute its differential. And write the integral in terms of the new variable. Then apply integration by parts with respect to the new variable. Please watch the separate discussions about the last two strategies for integration by parts. Now, let us discuss integration by parts for definite integrals. It consists of two major steps. First, apply integration by parts for indefinite integrals. Second, evaluate the result of integration using the fundamental theorem of calculus. Examples. Find the indefinite integral. Number 1. The integral of x times e raised to 3x dx. Solution. Apply integration by parts to make the integral easier to integrate. Let u equals x, which means du equals 1 dx. Meanwhile, let dv equals e raised to 3x dx. Get v by integrating using an exponential function rule with substitution. Where w equals 3x, v is equal to 1 over 3 times e raised to 3x. Afterwards, follow the formula of integration by parts. Next, rewrite the expressions to get a better look at the integral. The original integral now consists of a product term and an integral which is simpler than the original integral. Integrate the remaining integral, which has already been computed from the previous page. Add the constant of integration after solving the last integral. Then simplify by factoring out common factors. Therefore, the integral of x times e raised to 3x dx is equal to 1 over 9 times e raised to 3x times the quantity 3x minus 1 plus c. However, if the given integral is the integral of x times e raised to x squared dx, this can easily be solved using substitution rule. Let u equals x squared. Du is 2x dx, which means x dx is du over 2. Apply the substitution rule we just formulated. Then integrate using an exponential function rule. Substitute u equals x squared. Consequently, the integral is 1/2 of e raised to x squared plus c. Number 2. The integral of 4x multiplied by the sine of 3x dx. Solution. Let us apply integration by parts to make the integral easier to integrate. Let u equals x, which means du equals 1 dx. Meanwhile, let dv equals the sine of 3x dx. Get v by integrating using a trigonometric function rule with substitution. Where w equals 3x, v equals the negative of 1 over 3 times the cosine of 3x. Then follow the formula of integration by parts. Afterwards, rewrite the expressions for a cleaner look at the result. The original integral now consists of a product term and an integral which is simpler than the original integral. Integrate the remaining integral. Apply a trigonometric function rule with substitution. Add the constant of integration after solving the last integral. Simplify by factoring out a common factor. Thus, the integral of 4x multiplied by the sine of 3x dx is 1/9 of quantity 4 times the sine of 3x minus 12x times the cosine of 3x plus c. Number 3. The integral of the natural logarithm of x all over x raised to 4 dx. Solution. Use integration by parts to decompose the integral into a product and a simpler integral. Let u equals the natural logarithm of x, which means du equals 1 over x dx. Meanwhile, let dv equals 1 over x raised to 4 dx. Get v by integrating using the power rule. V equals the negative of 1 over 3x cubed. Then use the formula of integration by parts. Afterwards, rewrite the expressions for a cleaner look. The original integral now consists of a product term and an integral which is simpler than the original integral. Integrate the remaining integral. This integral has already been computed from the previous page. Add the constant of integration after solving the last integral. Then simplify by factoring out a common factor. Therefore, the integral of the natural logarithm of x all over x raised to 4 dx is equal to the negative of 1 over 9x cubed multiplied by the quantity 3 times the natural logarithm of x plus 1 plus c. However, if the given integral is the integral of the natural logarithm of x all over x dx, we can use a substitution rule to find the indefinite integral. Let u equals the natural logarithm of x. Du equals 1 over x dx. Then replace the integrand using the substitution rule we just formulated. Integrate using the general power rule. And substitute u equals the natural logarithm of x. Therefore, the integral is 1/2 of the square of the natural logarithm of x plus c. Number 4. The integral of the natural logarithm of quantity x squared plus 9 dx, from 0 to 3. Solution. Unlike other elementary functions, there is no integration rule for the natural logarithm function. So, let us try using integration by parts. Let u equals the natural logarithm of x squared plus 9, which means du equals 2x over quantity x squared plus 9 dx. The derivative is found using the chain rule. Meanwhile, let dv equals dx. Get v by integrating dv. V is equal to x. Afterwards, follow the formula of integration by parts. Next, rewrite the expressions. The original integral now consists of a product term and an integral that has a rational expression. Perform polynomial division to see if the expression can be decomposed into terms with known integrals. Integrate using a basic integration rule and an inverse trigonometric function rule. Because the integrals have now been cleared, proceed with evaluating the definite integral. Use the fundamental theorem of calculus to evaluate the definite integral. All terms in the second group becomes 0. Hence, the integral of the natural logarithm of quantity x squared plus 9 dx, from 0 to 3, is equal to 3 times the natural logarithm of 18 minus 6 plus 3 pi over 2. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.